Okay, later tonight, maybe around 11 o'clock, I'll give you a video on the modeling. I'll give you an idea of what we're going to talk about. Remember, they did a layup of one horizontal laid without tension, and then hoops this direction, 2 layers, and then, so 2 layers, 1 and 2, and then another horizontal layer. This layer is the one everyone imagines the sub, and I did put it on a tapered section for double reasons. But this is pretty rigid now. I've glued it tight. Now, so that's the reaction people think they see. As you can see here, what happens when I push down here? See the carbon fiber wants to react there. This piece is floating to help you see. You just don't get the one reaction that everyone says it just pulls the ends in. There's also an axis that this whole thing involves radius-wise that would have to also move. It's not logical. Now, I'll tell you why in a moment, because of using this cardboard. But now they sanded a lot of layers because they got out of alignment. It curved. So to get this back in alignment, they just sanded even, which means they broke tendons, or they cut down tendons, which changes the profile. It's no longer 2 to 1 ratio, 2 to 1 ratio, 2 hoops, 1 this direction, and again laid loose. This matters because it's not pre-tensioned. It's not post-tension, obviously. Well, maybe there's some post-tensioning on it during setting. So I made this up for you. You can look at it like this first. This is the vessel. This is pressure coming in equally everywhere. I could have I wanted you to visualize it this way. This is why you see it with the notches. But I could have just run another circle and said just all down. So just to help you visualize it. So this is point loading. This can't point load, right? Because it's water everywhere. 5,000 pounds PSI, let's say, everywhere. Just to round up. So if I try to push this down, I need to displace, and this needs to buckle out. So this side needs to go out. Well, I need this 5,000 pounds to displace 5,000 pounds. That's just a wash, right? It can't happen. But now I'm going to show you the profile where they did a lot of sanding, and this is the short version for you guys to get ahead of the game. The sanding creates this weird profile where you sand out layers. And so instead of it just being solid like you see here, you get the sanded layers. Now you get a different profile. That same pressure, let's say 5,000 psi, will react differently in that zone, giving it deeper penetration of deflection, if you will, inside here, which they only had limited amount of transducers and strain gauges. So the AI acoustic emissions monitoring to hear for fractures or not. But everywhere they sand it, they broke tendons. And that would be like me showing you this, and then I just start cutting away some of it. Alright, so what I did here also I want you to notice is that I started in the horizontal position over here, and then the hoop starts next. So that matters when you start the what the transducers are, because the transducers, if you look in there, the direction-wise, would be the strain gauges would be on top of this layer here, which is only connected to the layer below it, of course. Or were they on the hoops? Was that the first row? And the strain gauges are on top of that hoop. So how sensitive is that hoop compared to the lax version if it was the first layer was done in this capacity? How sensitive would it be? More sensitive. So what else do I want to show you here? So water coming in as it fractures. If one of these breaks up, water can come in and you can see you can just peel it off. That's one of the ways, and it just ejects this off. But we have this deflection happening, say around the rear of the vessel first, and I showed that with the bottle image where I show that if you look at the lighting or try to pay attention to lighting, let me see if I can get a different reaction there. Well, that sort of punches through. Let's let some air out of this so I get a different profile. I want it more along more of this direction. I had it working the other day, didn't I? So let me turn this down. So now, you see this right there? So this would be where it would first fold in. But it changes. See, now this is weak now, not the other side. This is weak, so this would fold it in. Fold it in, but it's also going to crush here. And now this is the end caps, which are going like this with millions of pounds of force on each end. They want to come in. They want to come in. And now when this buckles, when you see this, see that deflection there, we're using the lighting. When it buckles, it allows this end cap to now say, oh, I can defeat this now. But it can defeat it on one end. And I show you that, how it rotates using that model in the background, this one. I show you, okay, this is another model I'm working on for you guys. But I show you with this, that how we can get the end rotating in upon getting that deflection there, that failure, rotating in, pulling it off this lip here. It didn't just crush in, or it would have buckled the lip. We have a part of a lip that's in great condition, as we know in the videos. So, but down here we get a little different reaction, and I do that in other videos. What I'm showing you in this one is that I'm trying to model it for you to help you understand it. That these the sanding of these fibers were not for free. That the when they did the autoclaving, that the best they came up was about 352 psi. Now we got this piece right here, this section here, that came off. This is a significant section. A significant section came off. So as you can see, if I start laying this section onto a curved shape, we can start getting an idea of what this looks like. You're looking at it real time, obviously. But now we start putting back the pieces. I'm not saying that's the scale at all. I think this is only a 2-foot piece, maybe. I think it was the width-wise. But you look at this and you say, well, how does this edge so clean? Well, we see it fractured the other way. That means this side and that side turned in. All right, they turned in, and this piece says gets away scot-free. That piece name is Scott, incidentally, scot-free. So this was on a lathe, and then this is one of the videos I did for you guys live a long time ago. And I put multiple bands of tape on this, and different types of tape. And it's just tape on a can. So I can squeeze it, all things being equal, but not when I all of a sudden create more pressure here. Well, I'm not creating more pressure. What I have is a defect. No, I don't have a defect in the can. But there's a defect, well, maybe because of this profile there. But I'm creating a defect by pressing down. So it took me a while to press there. I mean, much more pressure than here because it is creased over there. But on this end, it's going to take a lot. Well, this end's not happening. It's got the interface ring. That is the can resisting my trying to stay at that lip. Okay. Now let's come in a little bit. So we come off the critical shear zone that's there. Let's come off. Still nothing. Here we are. So right now she starts giving me a response. And I'm here. I came that much in. So the edges are actually the ends are pretty damn strong because of the lip. All right, the interface ring, until it fails, of course. And then it's not strong enough. I made this model for you guys a long time ago, some of you that were participating back then. And I cut this out. This would be the interface ring, is what I'm trying to show, and the outer face ring. And this is the carbon fiber. This is equal pressure everywhere before we discovered that they sanded, that they took out fiber. So this is not continuous. These strands going wrapped around, around, around are not continuous. They ran across a wave like that, and they said, oh, we'll just fix that. Let's just chop it off. In essence, what they did when they sanded it down. or you can maybe see the wave better this way. And just chop it off. So you chop it off, and now you got to break a strand here, break a strand here. What strands did it chop off? Well, they even chopped off the horizontal strands, which actually give it its strong back, its ability not to fold in. If I were to glue this here, this becomes stronger, and I stack this up. This becomes stronger as a matrix with all the epoxy. Even going multiple layers here, I could change this to get stronger if I glued them together. These are not all glued. There's some glued here and some not. But I want to show you this is the 2 layers. Now, take note of how it's askew. And I visualize that that's part of those horizontal members are askew. I don't visualize them perfectly square with the face. If they were square with the face, it's still not 90 degrees because this was continuous tension. They would have to do individual bands. I'll go by 90 degrees, cut the tape, move over, whatever the lap is, go over, cut the tape, and it would have to be that way. But this was continuous wound. In that case, they are getting a slight skew here. With that said, that automatically, by default, even this was 90 degrees from here, this outside edge, and we have the skew, we do have an angle to speak of. And when they come back the other direction, like this, it's that angle. So there are 2 angles as it prints out the bobbin rolls back and forth, laying out the carbon fiber. But this is only 1, 2, stop. And then they laid 1 layer of this. And then they picked up again. So it would be down here or down here matters, but let's say they started here again. 1, 2, I started on this end. Now it stops. And they lay down the loose fibers this way. Loose meaning not tensioned. And then again, 1, angle that way, turn, turn, angle this way. So there is some multiple changes to directions, and if that's the pattern they used. And you get this, and we have these defects that they sanded out. So this is a precursor to the longer video. Just wanted to give it to you. Let you look at this, the difference now, the gradation of this. So let's say they sanded the top layer, right? And they sanded, 12 layers out. This is not to scale. It's just exaggerating a bit. Well, what happens? You've got broken. This notch represents no connection of fibers going across. You're actually looking at fibers behind it that have been ground down. The face fibers have been ground down. So if you could look at this, and I was to grind, and we look at it from this direction, it would look normal. As I grind off this top layer, you would still see this. As I made it even, you wouldn't see it. I think I have one of these loose for you to move it. Nope. I don't know. There we go. So now, I had this set up, but it looks like I set it. Okay. There it is. So now that's up there. Oh, we don't like it. So we grind it even. And now this fiber, you look down the profile and you see, oh, it's smooth. But in reality, you just cut this section out because it was buckled, or as they like to say, blistered. It's in a position there. To get rid of that, just take a sander to it until you get it flat. And if that cost you 1 fiber, if it cost you up to 12, I think he went up pretty high in numbers. Noodle time, and then I'm going to end. Noodle is going to tell us a little story too. I'll help you with the noodles another time. This one I've already shown you in another video, but what shows it better to me for you guys is this. Rapid Can, this is about $15 in tape. You believe that how expensive this stuff is? It's a really durable, it's not your standard tape. All right, it's not duct tape. It may look like duct tape, it's not. It's really a vinyl tape. It's got a lot of glue to it. See, at the interface ring, I can't do anything. See it? It's just too strong. And a little bit. Oh. Well, we're back to the can deflection here. I can't pull out this can. See, I can't pull it out. This is where it was in the vise of the jaws of the lathe when I made this up. And you can see the pattern as I went this way and that way. You see the pattern change the directions. And then they come back. And it's multiple different tapes, like I said. All right. So just wanted to help you understand that cutting the fibers, sanding the fibers down, you know, they keep saying, oh, it's going to take analysis. Well, just think of it as missing, you know, with this model. Just think of it as missing that you just deleted it. You just had a full continuous hoop, and even if they went down 3 layers, that means you went into the horizontal strength of it, which now you weakened it going down like that. So to say it's weak in the middle there, this is where you'd want to find in their carbon fiber that they were sanding in the middle, a lot of sanding in the middle. And this would be nice to know. Where do they sand? And you can profile it back. They have a lot of pieces. They can profile it back by taking this apart and finding out where they sanded in these layers. It may not look like much, but if you can continue this over, there's 133 pieces here, right? If you continue this over, you'll see they cut 12 bands. That creates that funky profile I told you about. And now this could move, so this could be no sanding on the outer one, which I think they did. You profile it based on this one they did. This is the end, so you can literally profile the sub from the 2 ends they have, and profile where you could draw up something like this. Profile where exactly, since they have the full ring, but they only took a segment out here, a cutaway. Not the photograph, but they literally just took a cutaway away. It was time. I think they could have profiled the entire ring. That's the existing sub that went down. That's Titan 2, that end piece. Yeah, this is Titan 2 because Titan 1 had a continuous, I believe. Titan 2 has the 133 layers. So they can literally profile with that. Okay, we got 10 fibers cut here. We have 8 over here. And you literally have the entire map, the entire section. And you map it. And now you look at it and look for the load path. Which one, if it was under equal pressure, where's the load path going to easily make its way back into the vessel? Verify it with the real-time monitoring system from the original dives and forward. And you will be able to map, oh, I know what's going on here. This since we got strain gauge and transducer sounding up over here, this matches up to our multiple locations, meaning make this one and this location with the profile of the sanding. So indicating here 7, indicating here 6, indicating here 3, and the only thing is bridging at that point is epoxy, but you also need to know what bands are you breaking. Are you breaking the longitudinal or the hoops? These are the tension ones, longitudinal when they do the cutting, sanding. All right, this video is that. Hey, again, I don't need your money. If you want to shout me out with some money, it goes to the cats. And I really appreciate you all doing that. I've seen quite a few donations there. And it goes to stray cats, too. I give them pills outside for the fleas and things like that. Hopefully this will give you a nice idea to understand how to start processing the sanding and the layers. All right, and why it matters and why that ring. They can still get hold of that ring. They can go back there short of the cuts they put in it. They can still get back in there the curved cuts, meaning the part the blades took out. They can profile the Titan 2, the original sub. They can profile the sanding, not just indicate that it was sanded. That entire ring will mirror, theoretically it only mirrors the ends. In the middle, there could be different sections too, but it will at least give you a good profile of the 2 ends and where that was left behind, that was connected to the Titan sub via epoxy / glue. And now the other thing I'm doing is I'm working on a field layout for you based on the debris placement. This is a hint. There's one piece of black carbon fiber that's curve shape that is, I'm going to kick this, that is 200 meters approximately from the main structure. This tells you what, the implosion was way up, the original delamination started high in the water column for this piece to be 200 meters away, I don't visualize this piece being at the bottom when an implosion happens and it's making it to 200 meters away under 500 psi. Now it can do it via it can't do it. It can't do it. So via, I'm going to say this, the military does have a bullet they shoot on the water. It goes about 50 feet. That's the best they can do. It works in its own cavitation. It gets in its own wake, if you will. It creates a wake, and then the bullet comes behind it, its own wake. And it goes about 50 feet under potential lethality. This would have to be the magic piece of carbon fiber that creates a wake and is able to go through 5,000 psi and go 200 meters away. It says curved. There's only black. There's only a few things black on there. That would be the back tank. There's it says carbon fiber. The back tank, I think, might be carbon fiber. And then we have the vessel as carbon fiber, and then we have the cross bracing between the legs. Not to be confused, the legs should not be confused with the skids. There's a difference. There's skids, and then there's the cross bracing, including the leg uprights. The leg uprights and the cross bracing that connects the two of them together at the bottom half are in great. They look great. They look awesome when they came out of the water. So it indicates that they were dropped. That it wasn't part of an implosion or explosive force. That they were dropped. Now, I had someone tell me that in the comments here. I'll just mention it. They said, "Oh, you keep telling us that the back end was ejectable." I hope, besides that person there, I hope none of you think that I said the back end was ejectable. The whole rear end was ejectable. I'm saying it fell off, meaning it broke off, it sheared off. Some force created this failure of the back end. I do not believe it was the implosion at that time. I could, if I get rid of that bias, I would have to go up about 2,000 feet off the deck. I did the calculations, and the skids are 9 feet 2 inches, 9.2 feet away from each other. The skids are. In the water themselves, they are. Hold on. Oh, I thought it. Oh, here it is. Gotcha. Hold on. In the water themselves, they are 22 meters apart. So here are skids, skid debris. Now debris is open for definition. Do they mean lead weights? But we also have a skid debris over here. So this is issuous for me. But behind the skid debris of this one and this one is the tail cone section presented to us, tail syntactic foam. And that's the wild card is up here. It says small black. I think it's right. Yeah, I magnified it. I magnified it, and I believe it says curved here, which is a real issue because the sub is down here, the main part. I got some delamination here. Drop legs, I believe it's here. Carbon fiber debris right here. What else we have here? Field debris, white debris. White debris would be the cowling or shrouds. All right, let me give you this one real quick. The thrusters, they did spell it thrusters, T-R-S-T-E-R, but I believe they mean thrusters. We got thruster here, and one here. We got two thrusters on this side. Well, because there's two thrusters on one side, so that it could have did a rotation here, and they didn't find a fourth thruster. Maybe it's over here out of their search range. This is out of their 200 meter mark. 200 meters from the skid center. I mean, from the last known location. It's interesting. Some of you don't know how I work, and what I do is for you guys,